Welcome all. I am Mr. B. George, Assistant Professor, Department of Pharmaceutics, Nirmala College of Pharmacy, Madhura. Today we are going to discuss about the topic theories of emulsification. So before we going into the topic, we should know what is meant by emulsion, what are emulsifying agents, and what is the real meaning of the sentence theories of emulsification. So first of all, we can start with the definition of emulsion. An emulsion is a biphasic system in which the liquids are uniformly distributed in another liquid or in another immiscible liquid stabilized by the addition of a proper emulsifying agent. I can repeat it again. It is a biphasic system in which there are two phases, both are liquid phases which are immiscible. For example, oil and water phase. One of the phases is uniformly and homogeneously distributed as globules or droplets in another immiscible liquid, stabilized by the addition of suitable concentration of emulsifying agent. And these emulsifying agents are those agents which are added to an emulsion to stabilize the emulsion. Okay. So there are mainly two types of emulsions, oil in water and water in oil emulsion. Whatever the emulsion must be, it is mandatory to add the emulsifying agent with suitable HLB as well as suitable concentration in order to make the emulsion stable. So as the definition says, emulsions are biphasic liquid preparations containing two immiscible liquids, one in which the dispersed as globules, that is the internal phase, and in the other liquid, that is the continuous phase or external phase, stabilized by the addition of suitable concentration of emulsifying agents. So from the first figure we can see that without the addition of surfactants or emulsifying agents, whatever mixing or intense mixing is done to an oil and water dispersion, after some times this oil and water will get separated due to the high instability or high energy conditions. So whereas in the presence of surfactants, these surfactants act as the emulsifying agents and form a coating over the oil-water interface or over the surface of a droplet, thereby decreasing the interfacial tension and the coalescence of droplets. And this results in the preparation or formulation of a stable emulsion. So next we can just see what is meant by the formulation of emulsion. So mainly there are three components in an emulsion: oil phase, aqueous phase, and emulsifying agents. Emulsifying agents are also known as emulsions or emulsifiers. As I already mentioned, emulsifying agents are substances or agents which are additionally added to an emulsion in order to make them stable. There are many mechanisms by which the emulsifying agents acts on an emulsion in order to make them stable. Stability in the sense means we are preventing the coalescence of droplets in an emulsion. Okay, here we are taking the example of a surfactant molecules as the emulsifying agent. As you all know, in a surfactant molecule there are two parts, hydrophilic head and hydrophobic tail. It is also known as polar head or non-polar tail. So from the word itself which is clear that hydrophilic head means polar. Polar means water loving, and hydrophobic tail means water hating or non-polar. Okay, so when it get oriented on the surface of a droplet or the oil water interface, the hydrophilic head will be facing towards the aqueous phase and the hydrophobic tail will be facing towards the non-aqueous or oil phase. And there is a balance between the hydrophilic group as well as the hydrophobic group in a surfactant, and that balance is commonly referred as hydrophilic lipophilic balance or HLB balance. Okay, higher the HLB value, higher will be the water solubility. Lower the HLB value, higher will be the oil solubility, and vice versa. So from the diagram it is clear that when we are adding surfactants as the emulsifying agent, they will get adsorbed on the oil-water interface or on the surface of droplets. And the orientation will be like that. The tail will be facing towards the oil phase and the head, polar head, will be facing towards the water or aqueous phase. These are the substances added to an emulsion to prevent the coalescence of globules of the dispersed phase and thus make them stable, as I already told us. All emulsifying agents concentrate at and are adsorbed on the oil-water interface. Oil-water interface in the sense means interface is the boundary existing between two different phases. In the case of emulsion, there are two phases, oil phase and water phase. And this oil-water interface is the boundary that is existing between the oil and water phases. That means, to be precisely, we are saying exactly on the surface of droplets. that is the oil water interface. And these emulsifying agents which we are adding will get concentrated on or adsorbed. It is not absorbed, it is adsorption, because adsorption is a surface phenomenon. These emulsifying agents will be get adsorbed on the surface of droplets, thereby making them stable and preventing coalescence. Okay, so as a whole, these emulsifying agents act in three ways, either of the three ways. One way is that by formation of a protective barrier over the surface of droplets. When we are adding emulsifying agents such as polymers or finely divided solid particles, they will get adsorbed over the surface of droplets and will form a rigid protective barrier or a coating over the surface of droplets, and thereby they will reduce the surface tension. Rather than more we can say that they will form a protective barrier that prevents the coalescence of droplets. Even if two or more droplets are coming together, they won't undergo coalescence or joining, because these emulsifying agents act as a protective barrier over the surface of a droplet. The next possible way of action of this emulsifying agent is by the reducing interfacial tension, and this is the mechanism by which surfactants act as emulsifying agents. So surfactants are agents that are added to decrease the surface or interfacial tension. When we are adding surfactants, they will get adsorbed on the oil-water interface, thereby reducing the interfacial or surface tension. So when the surface tension is reduced or interfacial tension is reduced, the surface free energy will get reduced, and when the energy get reduced, the system will become stable and they have less tendency to undergo coalescence. And the third possible way is that the decreasing the potential for coalescence by forming an electric double layer. If you are adding ionic surfactants means anionic or cationic surfactants, and these surfactants will form a coat over the surface of droplets, and these charges will make the droplets repel each other, so that if the droplets are coming together for coalescence also, they won't undergo coalescence because of the presence of charged surfactants on the surface of droplets. So these are the three possible ways by which an emulsifying agent acts. Out of these three mechanisms, the most powerful mechanism of stabilizing an emulsion by the addition of emulsifying agent is the reduction of interfacial tension by the addition of surfactants. So the first one is the formation of protective barrier. It is okay, but along with the addition of surfactants forming and reducing the interfacial tension, we can use the other emulsifying agents also as the auxiliary emulsifying agents, because primarily we are using a primary surfactant as the emulsifying agent. Along with that, if you are adding these polymers or any other finely divided solid particles, they will act as auxiliary emulsifying agents, thereby reducing the tendency, completely eliminating the tendency of these droplets to undergo the coalescence. Now we can come into the topic in detail, that is theories of emulsification. So emulsification is the mechanism by which an emulsion is being stabilized by the addition of emulsifying agent. So theories of emulsification explains the mechanism by which an emulsifying agent stabilizes an emulsion by the addition of suitable concentration of emulsifying agent. That is very important, because the concentration of emulsifying agent which we are adding is also plays a crucial role in the stability of emulsion. And based on the mechanism of stabilizing an emulsion, emulsifying agents are classified into surfactants, hydrophilic colloids, and finely divided solid particles. There are many methods by which we can classify the emulsifying agents. Based on the origin, we can classify natural, semi-synthetic, synthetic, and inorganic. And based on the HLB value also, we can classify the HLB according to the HLB scale of surfactants. And based on the charge, we can also classify anionic, cationic, non-ionic, and ampholytic surfactants. But based on the mechanism of action, these whole emulsifying agents can be categorized or classified into three categories. That is, first one is surfactants, second one is hydrophilic colloids, and third one is finely divided solid particles. Each these three categories have different or distinct mechanism of action, and this mechanism of action is the mechanism by which they are increasing or how they are making the emulsion stable. Okay, first of all, before going into the theories, just what is happening, we can look what is happening inside an emulsion upon mixing of oil and water phases. So if you are mixing oil and water phases, you know that oil and water is immiscible with each other. However, speed is applied by using a propeller or ultrasonic homogenizer, whatever if you are applying also, the large droplets will be split into smaller droplets. And when the number of droplets increases, the surface area will get increased. And when the surface area gets increased, the interfacial tension will get increased. When the both surface area and interfacial tension is increased, that will result in the increase in the surface free energy. Actually, surface free energy is defined as the work done to increase the surface area of a droplet by 1 unit. Okay, that is meant by surface free energy. And we know that if higher the energy, the system will be more unstable. So what will the system will do? They have the tendency to become stable by merging or by reducing the surface area by coalescence. So this is actually what is happening in an emulsion if you are not going to add an emulsifying agent. Again, I will say that if you are mixing oil and water phase, both are immiscible with each other. However force or however speed we are applied for a mixer, after mixing, these oil and water will get separated as distinct or separate layers, which will make the system unstable. And the mechanism behind this is that when the droplets are being cut into very fine droplets upon mixing, the surface area will get increased, and when the surface area increases, interfacial tension will get increases, because surface area increase the interfacial tension will also get increased. This will result in the increase in the surface free energy, and the system will become unstable. High energy system means the system is more unstable. So naturally the system have a tendency to become stable by undergoing the coalescence of droplets. So by undergoing coalescence, the small droplets will become large droplets, which will in turn decreases the surface area, which will in turn decreases the surface free energy, and the system net free അല്ലെങ്കിൽ net work done to increase surface area will get reduced. That is reduced in the surface free energy, and the system will become stable. And this system will become stable means they are undergoing phase separation. The oil which having a low density than of water will be remaining on the top, and the water phase which have higher density than of oil will be remaining in the bottom. And this is what happening in a emulsion if you are not going to add an emulsifying agent. So we are adding either surfactants or hydrophilic colloids or finely divided solid particles in order to make the system or emulsion stable. So let's see one by one how they are going to act upon the addition in an emulsion. So based on the nature of the film formed at oil-water interface, the mechanism of action of emulsifying agents are classified as monomolecular adsorption or interfacial tension theory, multimolecular adsorption or viscosity theory, and third one is solid particle adsorption or film theory. So we are categorizing the emulsion based on the mechanism of action, and based on these mechanism of actions, three distinct theories are being developed. That is, first one is interfacial tension theory, second one is viscosity theory, and third one is film theory. From the word itself, we can say that interfacial tension theory is based on the reducing the interfacial tension on the oil-liquid interface, and we know that a surfactant is able to decrease the interfacial tension, making the system more stable. So from the word itself, it is clear that in the first theory, that is interfacial tension theory, surfactants are being used as the emulsifying agent, which will form a monomolecular adsorption layer over the surface of droplets. Second one is viscosity theory. Surfactants has nothing to do with the viscosity, they will only reduce the interfacial tension. So in order to increase or decrease the viscosity, or here we are going to increase the viscosity. When the viscosity of the system is increased, the kinetic property, that the movement of the globules will get decreased, and there are less chances of coalescence. So this viscosity can be increased by the addition of polymers. Okay, that is called as multimolecular adsorption. That means in the case of surfactants, they are only forming a single layer over the surface of droplet, that is the monomolecular adsorption theory. In the case of viscosity theory, we are going for the addition of polymers to increase the viscosity, and these polymers will form a multimolecular layer or coat over the surface of droplets. So that is the difference between surfactants and polymers. Surfactants will form a single layer over the surface of droplets, that is called as monomolecular adsorption. In the case of viscosity theory, we are adding polymers, and these polymers will form a multimolecular layer over the surface of droplet. Multimolecular means more than two layers. And the third one is film theory, and in this case we are adding finely divided solid particles such as bentonite, talc, etc., which will form a film over the surface of droplets. That is called as solid particle adsorption or film theory. Okay, let's see what is meant by monomolecular adsorption in detail. The surfactant stabilizes the emulsion by two ways. We, as already said, here we are adding surfactants which will form a monomolecular layer. So when we are adding these surfactants will make the emulsion stable by two mechanisms. First one, by reducing the interfacial tension existing at oil-water interface. As I already mentioned, surfactants are primarily used to reduce the surface or interfacial tension, thereby reducing the surface free energy and making the system stable. Second mechanism is ionic surfactants, which means charged surfactants such as anionic surfactant or cationic surfactants. If we are not using a mixture of surfactants such as anionic as well as cationic surfactants. Either we are using anionic surfactants or we will go for using cationic surfactants. If both surfactants are used together, they will merge together and the system will become neutral. So there won't be any effect on the stabilization of emulsion. So here we are using either anionic surfactants such as sodium lauryl sulfate or cationic surfactants such as cetrimide, benzalkonium chloride, etc. Okay, so ionic surfactant impart charge on the surface of droplet which will cause repulsion. So when these ionic surfactants are used, they will form a monomolecular layer over the surface of droplets and will develop a charge, either positive charge or negative charge. And when these molecules or globules will approach together or comes together, these like charges get repelled and the system will become stable by not undergoing coalescence, because even if the globules will come together, they will get repelled due to the presence of like charges on the surface of droplets. And let's look what is meant by Bancroft rule. Bancroft rule is related to the HLB value of emulsifying agent, that is surfactant. So according to the Bancroft rule, it is saying that the phase in which the emulsifying agent is more soluble will form the continuous or external phase. For example, twin 80 having a high HLB value will form oil and water emulsion. So I think we are all thinking about that. If you are going for the preparation of oil and water emulsion, water will be in the higher concentration and oil will be in the lowest concentration. No, it is not like that. The type of emulsion which is going to happen or which will be developing is mainly depending upon the HLB value of the surfactants which we are going to select as the emulsifying agent. So if you are selecting a surfactant which is having a higher HLB value in the sense means the surfactant will be more soluble in water. Okay, when the surfactant is more soluble in water, the water will form the continuous phase. Okay, and reverse is happening in the next case also. If you are using a emulsifying agent or a surfactant which have a low HLB value, it will be more soluble in oil phase. So the oil phase will be the continuous phase, that is we will get a water in oil emulsion. That is what the Bancroft rule says. The phase in which the emulsifying agent is more soluble will form the continuous phase. I think there are two or three methods of preparation, a dry gum method, wet gum method, etc. If you are going to prepare for oil and water emulsion, I think in the case of liquid paraffin emulsion, we are going for acacia. Acacia is used as the emulsifying agent. Acacia is more soluble in water phase. So in the case of liquid paraffin emulsion, we are going to get a oil in water emulsion. Okay, the same is in the case of castor oil emulsion also. There also we are getting oil in water emulsion because acacia is used as the emulsifying agent in castor oil emulsion. Even tragacanth also, if you are using as an emulsifying agent, it is a polymer which is more soluble in water than that of oil. So there also the emulsion will be forming as oil in water emulsion. So that is what the Bancroft rule says. According to Bancroft rule, the phase in which the emulsifying agent which we are selecting is more soluble will form the continuous phase. Higher the HLB value, it is more soluble in water, hence the water will form as the continuous phase and you will get a oil in water emulsion. Okay, twins are almost having high HLB values and they have a more water solubility than that of oil solubility. So if you are going to prepare an oil water emulsion, we can go for the taking twin 80, etc. Okay, in the case of spans are surfactants which are more soluble in oil than that of water. So if you are going to prepare a water and oil emulsion, we can take span 80 or spans as the sorbitan esters, that is span as the emulsifying agent or surfactants to prepare a water and oil emulsion. So this monomolecular adsorption theory or film theory that we can explain by seeing the three diagrams. Let's go through the three diagrams. First diagram is showing an emulsion in which the surface of the globules or the film that is formed by the surfactant, which is an external emulsion that is having close packing and complex film, because we are adding sodium cetyl sulfate which is having a negative charge and cholesterol which is having a positive charge. So when we are both using the combination, that is sodium cetyl sulfate is an anionic surfactant, cholesterol can be used as an auxiliary emulsifying agent. When both these combinations of emulsifying agents are used together, it will form an excellent emulsion due to the close packing and complex film, because we can see from the figure itself they are having a closely packed appearance. There is not even a vacant space on the surface of droplets, so we will get an excellent emulsion in the case of first one. In the second diagram, it is showing a poor emulsion, loose packing, because the packing is not uniform and these molecules, surfactant molecules, are not closely packed. So the film formed is non-uniform. That will result in the formation of a poor emulsion. So we are using a combination there in sodium cetyl sulfate along with the oleal alcohol. They have a less complexation as well as the poor packing, so we will get a poor emulsion. In the case of diagram C, there also we are getting a poor emulsion. Even though it is having a somewhat closely packing, they are having negligible complexation, because there we are using a combination of cetyl alcohol and sodium oleate. Sodium oleate is having a negative charge. Even though we are seeing a uniform packing between the emulsifying agents over the surface of droplets, they have a negligible or very less complexation. So the film formed will, even though the film formed is a uniform film, there are chances of rupture of films, or these films are unstable because they won't exist for a long period of time on the surface of droplets. So there we are also getting a poor emulsion. So from these three diagrams explains are examples of a film theory, that is monomolecular adsorption theory. Monomolecular means a single molecular layer is formed on the surface of droplets, and this layer is formed by the addition of surfactants as well as auxiliary emulsifying agent. In the first case, sodium cetyl alcohol is the surfactant that is negative charge, so it is an anionic surfactant. Along with that, we are also adding cholesterol as auxiliary emulsifying agent in order to increase the stability. Okay, and the first one is giving an excellent emulsion because they are not only having a very uniform close packing, but also they are also undergoing a complexation between sodium cetyl alcohol as well as cholesterol. In the second and the third diagram, that is B and C, we are getting a poor emulsion, because if it is having a close packing, it is not having a proper complexation, and if it is having a complexation tendency, if the packing is not uniform also, we are going to get a poor emulsion. So I think it is more clear when showing this diagram and explaining. So that is all about monomolecular adsorption theory or film theory. So in the diagram we can see the three theories: monomolecular film theory, multimolecular film theory, and solid particle film theory. In the case of monomolecular film theory, already explained, we are using surfactants, and a single layer of surfactants is only formed. Even if we are adding much concentration of surfactant, a variety of surfactant also, they are only forming a single layer, that is known as monomolecular film theory. In the second case, multimolecular means we are adding polymers. Polymers will form multimolecular layer, that is a layer over the other they are forming, and they are more rigid, but they won't decrease the interfacial tension, they only increases the viscosity as well as form a protective barrier over the surface of droplet. Third case also, addition of solid particle, they are also forming a protective barrier over the surface of droplets. They are having no action regarding reducing the interfacial tension. So next one we can look in detail, multimolecular adsorption theory. Here we are adding hydrophilic colloids or hydrophilic polymers, which forms a multimolecular film around the dispersed droplets in an. So hydrophilic colloids form multimolecular film around the dispersed droplets, and which results in the formation of oil and water emulsion. So one thing, it is clear that in the case of multimolecular adsorption theory, we are using hydrophilic colloids or hydrophilic polymers. From the word itself, it is clear that they are more water soluble than that of oil soluble, and we will go for the preparation of oil and water emulsion according to Bancroft rule. So there are many examples of hydrophilic colloids or polymers, that is acacia, tragacanth, gelatin, etc. And they mainly act by two mechanisms: either they will increase the viscosity or they will form a protective barrier. Both they are doing, because if you are adding a water soluble polymer to a water, they will undergo swelling, and this swelling will increase the viscosity of the system. Moreover, they are also forming a protective barrier over the surface of droplets, thereby decreasing the chances of coalescence. This is all about the mechanism by which the hydrophilic colloids forms multimolecular layer over the surface of droplets, thereby increasing the stability of emulsions. So again I can say multimolecular adsorption theory is mainly related to the preparation of oil and water emulsions. And here we are adding hydrophilic colloids, which means polymers which are more water soluble. For example, acacia, tragacanth, gelatin, etc. Hydrocolloids stabilizes the emulsion by two mechanisms. They will increases the viscosity. When the viscosity of the system increases, the movement of the droplets will get reduced and there are less chances of undergoing coalescence. And also second mechanism is that they will form a protective barrier over the surface of droplets, thereby decreasing the chances of coalescence. Even if the droplets come together also, they won't undergo coalescence. So this is the mechanism by which the multimolecular adsorption theory explains the mechanism by which these emulsifying agent, that is the hydrophilic colloids or polymers, will make the emulsion stable. Okay, the third one and the last theory is solid particle adsorption theory. Here also we are adding finely divided solid particles such as bentonite, vegan, etc. They also have nothing to do with increasing the viscosity or decreasing the interfacial tension. They just act as a mechanical barrier over the surface of droplets, thereby preventing the coalescence. Actually, these finely divided solid particles are not used alone in the preparation of an emulsion because these emulsifying agents are very less active as compared to that of polymers as well as surfactants. So, these will act as an auxiliary emulsifying agent. That is, the finely divided solid particles such as bentonite and vegan act as auxiliary emulsifying agents. That means these are only used in combination with the true അല്ലെങ്കിൽ primary emulsifying agents. So example bentonite and vegan. Again I can say finely divided solid particles in the sense means they will also form a multimolecular layer or a coating over the surface or a mechanical barrier over the surface of a droplet, thereby decreasing the chances of coalescence. Here these particles have nothing to do with the interfacial tension and nothing to do with the viscosity. So these are the three mechanisms by which the three different types of emulsifying agent, that is the surfactants, hydrophilic colloids and the finely divided solid particles acts in an emulsion and making them stable. So these are the things or the physics or mechanism behind the emulsifying agents, how they are going to make the emulsion stable. So we can summarize the theories of emulsification. Emulsion, you know, it is a biphasic system which consists of oil phase, water phase, and we are adding a suitable concentration of emulsifying agent in order to make the system stable. So here about the theories of emulsification, these theories explains the mechanism by which an emulsifying agent makes the emulsion stable. So there are three types of emulsifying agent we are using in an emulsion to make them stable, that is surfactants, hydrophilic colloids or finely divided solid particles. Either they are used alone or in combination with each other. So if you are using a combination of surfactants or this combination of emulsifying agent, there are more chances to get a stable emulsion. And according to Bancroft theory, the phase in which the emulsifying agent is more soluble will form the continuous phase. So based on the theories of emulsification, there are three types of emulsifying agents we are using: surfactants, hydrophilic colloids and finely divided solid particles. In the case of surfactants, it is going to form a monomolecular film over the surface of droplet, thereby decreasing the interfacial tension, which will result in the decrease in the surface free energy, and the system will become more stable and less tendency of coalescence. In the case of hydrophilic colloids, these are actually polymers which are soluble in water, for example acacia, tragacan, gelatin, etc. If you are adding polymers, they will go into the water phase and they will get swelled, and upon swelling the viscosity of the system is increased and the movement of the droplets will get reduced, thereby reducing the chances of coalescence. They are also forming a multimolecular layer or a protective coat over the surface of droplet, thereby again decreasing the chances of coalescence. And third one is finely divided solid particles. These are actually auxiliary emulsifying agents. In the sense means auxiliary emulsifying agents are those agents which are added only in combination with the true emulsifying agents such as surfactants and hydrophilic colloids. If we are adding finely divided solid particles, they are also forming a protective barrier or a coat over the surface of droplets. They have nothing to do with viscosity as well as reducing the interfacial tension. That is why they are not used alone in an emulsion. They are only used in combination along with the true emulsifying agents. So that's all about the theories of emulsification. Hope you all understand. So before winding up, I can also say some examples regarding the surfactants. Surfactants are many types: anionic, cationic, non-ionic and ampholytic. Example of anionic surfactants include sodium lauryl sulfate. Anionic means these surfactants are having a negative charge, predominantly negative charge. For example, sodium lauryl sulfate and other soaps. Example for cationic surfactants includes benzalkonium chloride, cetrimide, benzethonium chloride, etc. These are predominantly having positive charge upon ionization. And non-ionic surfactants are surfactants which are having no charges. For example, twins, spans, etc. Twins means polysorbate, spans means sorbate and esters. And ampholytic surfactants which will form sweeter ions upon the difference in algae, they will form positive as well as negative charge depending upon the pH. For example, lecithin. And second one, hydrophilic colloids. Hydrophilic colloids are actually polymers which are more soluble in water. For example, acacia, tragacanth, gelatin. And third one is finely divided solid particles. For example, bentonite, vegan, talc, kieselguhr, alumina, etc. So that's all about the theories of emulsification, types of emulsifying agent based on the theories of emulsification as well as their examples. Hope you understand. Thank you.